Hello folks. Okay, I want to talk a little bit about heap management this time around. So again, this is another one of the things that a compiler writer has to be cognizant of. How are we managing the dynamic allocation and deallocation of memory? So we have to be aware of what's going on our system and what the language is expecting in terms of behavior. So I just want to discuss a number of the different questions that kind of surround this. So again, our compiler has to address the language's memory management plan. Is the programmer under the language allowed to explicitly request and free memory? The sort of C-ish mallocs and callocs and frees and whatever explicit allocation and deallocation tools are provided to the programmer. On the other hand, for a lot of languages, all of that is handled kind of implicitly behind the scenes without programmer interaction. And if you've got typical object-oriented languages, the objects are getting created in the heap someplace and freed up in the heap someplace, and that's being managed for the programmer, but it's still something that the compiler writer has to be aware of, right? How is this taking place? So, a few things that we want to take a look at. Garbage collection. Is it automated? Is it scheduled? If it's scheduled, how is it scheduled? Is this intermittent, or is this when we run out of space, or what's the deal? Is there any kind of built-in protection provided against memory leaks, against dangling pointers? Right? What are we supposed to be providing for the programmer, and how are we going to do that? If the programmer does request a chunk of memory, how do we go about picking one and allocating it? Right? How much of that is our decision and how much is interaction with some routine provided by the operating system? So those are questions we want to answer. Again, when memory is freed, how does that get returned to the free pool? Right? Whatever collection of free space that you've got. What happens when free memory gets low or gets broken up into tiny fragments where none of them are particularly usable? Right? They're all too small to be used for the things that we're doing with our programs right now. So these are all things that we want to try and address. So I'm going to take it from a kind of high-level perspective in this one, and then in the next couple of sessions we'll go in and look at some specific approaches and techniques. All right, in terms of the allocation and deallocation side of things, right? We've got either the programmer explicitly saying, please give me this and now please free it up, or we've got it happening implicitly, but either way, we've got to maintain some kind of pool of the chunks of memory that are free and available to be requested. When a request comes in, we've got to pick, out of those free chunks, which one are we going to use to satisfy the request? And again, there's a lot of different algorithms. You've probably talked about this in the operating systems course as well. Can you go through and take first fit? So if you've got this kind of list of chunks, then just the first one that's big enough, grab it and use it. Or best fit. We'll go through and find the one that's the smallest one that's big enough. So we've got the smallest amount of leftover space afterwards. Or we'll go through and take the worst fit. Just take from the biggest existing free chunk. So best fit versus worst fit, you're either using something that's closest to the right size, or you're using something that's going to leave the biggest chunk of free space available afterwards. So all sorts of different rationales for picking these algorithms. Again, we'll take a look at some ideas in specific in the next couple of sessions. Again, when we deallocate it, we need to be able to return this thing to the free pool. And if the chunk that we freed up is right next to another chunk that's free, do we kind of group the two of them together to create one big free chunk, or do we leave them as kind of two free smaller chunks? So all sorts of issues that we want to think about, both on allocation and on deallocation. And again, we'll take a look at a specific approach in the next couple of sessions. Now, if we've got an item that's been allocated and later it gets freed up, well, let's say it's been allocated and we've just got one pointer or one reference to that item. So there's only one thing referring to that item wherever it is off in memory. It's easy to tell when that memory should be freed up, right? When that one item goes out of scope or does an explicit delete, then we can say, okay, that's fine. It's time to get rid of that thing in memory because the one thing that referred to it is gone. But if we've got a language that allows us to have multiple references to the same item, how do we keep track of when the last one disappears? If I've got 5 or 6 or 12 different pointers to a particular object, how do I know when it's safe to delete that object? How do I know when there's no more pointers pointing to it? Right? We have no idea, how often the programmer is copying pointers back and forth, or where the programmer is remembering an offset to something and saying, oh well, it's this that object is this many bytes from this address. So it can be very difficult to figure out exactly when we should go through and deallocate that item. So some of the things that we want to take a look at are approaches to automatically keep track of when there's nothing left referring to a particular item, and as soon as we reach that point, we'll delete the item. So this is kind of as soon as we can, we get rid of it, and we put in extra steps to be able to do that. Or we take an approach where we say either every so often, or when memory gets low, or when the programmer asks us to, we'll make a sweep through all of the things that are out there and see if we can figure out which ones still have pointers to them. And we'll keep those, and anything that we can't find a pointer to, we'll just delete. So there are a few different options that are available to us, and they've got advantages and disadvantages. So these kind of sweep algorithms have the goal of going through, and if there's no longer a reference to something, we'll get rid of it. So this kind of implicitly gets rid of memory leaks, because we're going through and saying, okay, well, if you've lost track of something, we're going to get rid of it for you. So one of the things we can do is keep a kind of administrative pointer to all of the things that are off in the heap, and we'll go through and mark each one of those things as unreferenced. So we'll just keep a little flag associated with them, and when we do our sweep, we'll go through and say, okay, we'll treat them all as unreferenced for now. And then we'll go through all of the active pointers that are currently in the program that we're analyzing, and for any of them that refer to one of those items in the heap, we'll tick that item off as being referenced. So we go through all of the available pointers and see which things are being referred to. Once we've done that, then we go back to this list of all of our allocated items, and anything that still says it's unreferenced, we can delete. And so this is kind of one approach to going through and saying, okay, we'll just see if we can figure it out when we decide to run it. And again, this can be run at fixed intervals. It can be run on demand by the program. It could be run automatically if a memory request fails, or if free memory drops below some specified threshold. And so there's a bunch of different ways we could trigger how and when to run an algorithm like this. The other approach is the kind of smart pointer approach, where instead of having just a blind pointer to whatever the item is in the heap, what we'll do is have a smarter object, a more advanced object. When we allocate an item in the heap, we'll go off and create the space for it, and in this sort of smart object, we'll put the actual pointer into the heap, and we'll start a count of how many programmer pointers are referring to this object. And so every time a programmer copies this pointer from one to another, we'll bump up that count. And every time they change a pointer to point to something else instead of this object, we'll decrement this count. If the count ever hits 0, there's nothing left referring to the item, and we can delete it from the heap. Usually we'll probably keep that smart pointer object around just in case the programmer has left some kind of dangling references to this thing. But we can go through and, in this manner, have a way to identify how many things right now are referring to given items. Now, this does mean that you've got this kind of layer of indirection. When the programmer thinks they're accessing a pointer to an item, it's actually going through this extra step, through this intermediate pointer. But it gives us some protection against memory leaks, against dangling pointers, so a variety of different pointer problems. One of the other issues that we might consider is, what do we do when our free memory gets too fragmented? As the programmer is going through, making requests and freeing them up, and making requests and freeing them up, you're, grabbing chunks of memory space and freeing it up, and grabbing chunks, and these chunks are gradually sort of getting pulled out of memory and dropped back into memory. And you might find that memory is getting carved up into smaller and smaller and smaller sections of free space, where you've got however many bytes of free space, and then a chunk that's in use, and then a bunch of bytes of free space, and then a chunk that's in use, and a bunch of bytes of free space, and a chunk that's in use. over the course of time, you can wind up with a lot of tiny chunks of free space. So if you put them all together, you'd have enough space to do something useful and to service most requests. But because they're so broken up, each individual piece is too small to be useful. So one of the things we can do is periodically go through and say, okay, let's take all of the allocated chunks that are out there and move them all into one contiguous block. And then we've got this sort of chunk of all the things that have been allocated, and then this big chunk of free space. And we can start reusing that chunk of free space to work with more effectively. Now, the only problem there is that, of course, there's the overhead of actually taking the time to stop and move all of these contents. Right? We're copying everything that's currently allocated. It means that we've got to have a kind of a free section of memory someplace to move these things to. But it does give us some flexibility in this. The other problem here is if the programmer has, if this is something like C, where the programmer's got their own pointers into memory, then when we move things, their pointers are no longer pointing at what they thought they were. So there are issues with an approach like this if the programmer has manual control over their own pointers. Now, an approach like this might work well if you're using smart pointers, because again, we can just redirect where the smart pointer is pointing into the heap, and the programmer is none the wiser. But if you're allowing the programmer to use the sort of C-ish dumb pointers, if you like, then we do have issues here. All right, those were the kind of key points that I wanted to bring up. And again, what we'll do in the next couple of sessions is look in more detail at some possible allocation approaches and deallocation approaches.